Hey guys, I know we've been discussing about tensor and we have reached a critical stage in tensor wherein we want to understand how a tensor representation can be made coordinate independent or independent of the frames of reference. So that is where we stand. But what we are going to do in this lecture is, or in the upcoming few lectures is, we would be taking or we would be digressing from our original path and consider something totally different. Of course, it is for some logistic reason I have to do it, but still we will consider this to be rather a welcomed distraction, and we will see where it leads us. All right. Now, if you are someone who is interested in materials research or who has been in materials research or who are seriously considering materials research, even if you have spoken with someone who is pursuing materials research, it is possible that you might have heard of the term density functional theory. So this is something that is quite recently gaining ground, primarily because of course, it's a wonderful theory. I don't know, maybe because of my over enthusiasm, I'm writing it twice. So this is the theory that you might have heard of, density functional theory, and it's gaining ground primarily for one of the reasons is that the computational resources that are at our disposal is quite increasing. We are able to use them extensively, and so for that reason as well, we are allowing this theory, or we are using or adapting this theory to understand certain behavior of materials. Now, what we will do in this and the subsequent lecture is that we will be trying to understand some bits and pieces of this density functional theory. Of course, we will not be considering all the nuts and bolts that are involved in it. We will not be digging deep into it. You have to remember that this is not a course on density functional theory, which we are considering this as a part of our mathematical technique course. So the primary reason here why we consider density functional theory is that we want to make ourselves acquainted with this theory. So that is the primary reason. So when someone talks about using the theory, so you feel comfortable listening to their conversation or listening to them present their result. At its foundation, the density functional theory is nothing but calculations that involve quantum mechanics. Now, if you see here, this is just an illustration of the different aspects of physics, and as you can see, quantum mechanics, it holds its own position. Now, again, just being a representation or an illustration, we cannot assume that all the mentioned information are accurate. So everybody should agree with the different aspects of this illustration. The illustration I'm talking about is this one. So we need not agree ourselves or be comfortable with all the different description that is given here. But of course, these are the different fields of physics, and now what we essentially want to do is we want to see how we can use this amazing field of quantum mechanics to our benefit as a materials researcher or researchers who deals with metals and materials. For that, we need to begin by defining quantum mechanics. If you are not from a physics background, possibly this is one of the few times that you will consider quantum mechanics. So let's start from the basics. We will define what quantum mechanics is, at least for our purposes. So in this illustration, the quantum mechanics is stated as dealing at the length scale that is around or below 10 to the power minus 9 meters. So of course, we refer to this as nanometers, and if you are familiar with materials, we have something called as nanomaterials, and we have studied them, or we are studying them extensively. They serve a wonderful purpose in our application, so we are considering them, we are looking at them rigorously. So there are so many teams of researchers who are interested in that. And even though we are looking into them so rigorously, and we are trying to understand them, analyze them, and put them to use, it is not so often that we try to understand them from the quantum mechanics or from the basis of quantum mechanics. We look at them as any other regular material. We talk about their arrangement, we talk about their evolution, we talk about their behaviors, we talk about their strength, their properties. Very rarely we consider, of course, quantum mechanics or rather nanomaterials is studied from the perspective of quantum mechanics, starting from the quantum mechanics. But as materials researchers, very rarely we have an exclusive focus on nanomaterials from quantum mechanics. So therefore, this definition, even though it might seem appropriate to in certain circles, as far as the material research goes, this is a very elaborate description of what quantum mechanics mean to us. So in order to define the quantum mechanics, let's go to rather a person with whom we are familiar with. If not, we will be made to know him, or we are made to know him. So in one of his discussions, particularly when he was considering this field of quantum mechanics, which was at that time emerging, the way he described quantum mechanics, or the way he talked about quantum mechanics, was, of course, it was not in the positive connotation. The way what he said was, the old one doesn't play dice, meaning the God doesn't play dice. So what he essentially meant was, when the quantum the foundation of the quantum mechanics essentially involved a lot of probabilistic calculations. If you consider Heisenberg's uncertainty principle, I guess it was a letter written to Heisenberg wherein it states that, saying God doesn't play dice. I mean, if you believe in God, it doesn't really matter, but material usually behave, the physical system usually behave in a deterministic way. There is not much probability involved in the physical world. So that was his understanding. And when the quantum mechanics begin to emerge, it sort of shook his foundation. It sort of involved a lot of probabilistic approach. So he was not comfortable with it, and so he made this claim. So as we are considering the different mathematical techniques that are involved in materials research, what fundamentally changes when we begin to consider quantum mechanics is that we are going to involve probability much more than in other contexts. So all the other formulations that we have been considering, essentially they were deterministic. When this is what is the causal agent, there is going to be some response. So all this, this is going to happen. These were deterministic, well determined, well defined using mathematical formulation. But when you get into quantum mechanics calculation, or when your calculation involves quantum mechanics, you are going to rely on probability. So that is the key distinction that separates all the other mathematical techniques that are involved in materials research when compared to the role of, or the way we differentiate quantum mechanics. So like I said, our goal is not to get into the quantum mechanics calculation. It is not even to dig deeper into the DFT calculations, and density functional theory. It's just that we are in this context of mathematical techniques. We have considered different approaches. We have started with ODEs, we have considered PDEs, we have been considering tensor notations, so involving vectors. So while we are doing this, we have considered gradient and all those things. So while we are doing it, we also want to extend our reach to quantum mechanics. So that is one of the primary goals. Quantum mechanics, why not? And DFT calculation is the ideal, it gives us the ideal segue for it, meaning we are going to use quantum mechanics or the calculations in the framework of DFT. Of course, there are going to be numerous approximations that are involved, but still, we are involving some portions of quantum mechanics to our benefit, and that's the reason why we are considering quantum mechanics along with, or in the context of DFT, in mathematical techniques and materials research. So I guess this is rather the introduction of what we are about to do in this lecture and the subsequent lecture. Now when you consider, let's say, a material like this. Now of course, those of you who are already familiar with materials, you would, when you see this representation, and when I say that this represents a material, you would naturally claim this to be a crystalline material, because what you see is a regular arrangement of the atoms. The property that emerges from this material is rather the combination of two things. As we have represented it, the property that emerges from this represented material, of course, it's a two-dimensional representation. What you observe is just a few features of the material. One is it is regularly arranged. You see a regular pattern to it, and the atoms are spaced equally. So of course you can again include it in the regularity, but here in the atoms are spaced equally, there it's regularly arranged. So this arrangement of the atoms influences in the macroscopic scale the property of the material. So when I change either the configuration of the atoms or the distance between the atoms, I'm going to ultimately change the property of my material. So of course these arrangement or the configuration of the atom is what we refer to as the crystal structures. So if there are two metals with the same crystal structure, let's say face-centered cubic crystal structure. If there are two metals with the same face-centered cubic crystal structure, FCC metals, the difference in their properties, when you, let's say, stretch them, the difference in their strength essentially stems from the distance between the atoms. Their configurations, the way they are arranged is the same, but the only key difference is the distance between the atoms is different. So it's not only how the atoms in a given materials are arranged that determine the property of the material on the macroscopic scale. So this is just an atomistic arrangement, but also the distance between the atoms. So these distances between the atoms also play a key role. So this interatomic distance, let's say d, they also play a key role in determining the property of the material. Now, is there any possible way for us to calculate this d from a theoretical foundation without doing any experiments? Is it possible for us to calculate this interatomic distance? So that is what we are going to explore, because unknowingly, or sometimes even knowingly, we have been doing some quantum mechanics calculation, at least in the foundational level. We have been rendering some quantum mechanics calculation, at least in some basic level, while we are dealing with this crystal arrangement and the interatomic distance. And that is where we are going to start, so that we can build on it. So what we are essentially going to do in this lecture is, we are going to start from a point which we are familiar with, wherein we have been using quantum mechanics calculation. And that point is this: we have regular arrangement of the atoms. In the regular arrangement of the atoms, the property of the material that constitute these atoms depend also on the interatomic distance between the atoms. Now the question is, will we be able to calculate this interatomic distances starting purely from a theoretical standpoint? So that is what we are going to see. And if we are able to do so, what is governing? So what is the math behind it? Is what we are trying to understand here. Now, instead of considering the material as it is, this particular configuration of the material, let's begin by considering or taking into consideration the pairwise interaction of the atoms, something like this. So instead of considering the entire set of atoms, let us consider something like this, which is referred to as the pairwise interaction. So we are just considering one pair of atoms, not the entire array of atoms or the entire lattice of atoms. Now, when we consider pairwise arrangement of the atom, is just the one-dimensional representation, meaning I cannot play around with the configuration of the atoms. All that I'm considering is two atoms. When I have just two atoms with me, I cannot essentially change my configurations in any meaningful way. All I can do is change the distance between the atoms. So what I'm essentially then changing is changing the interatomic positions. So when I change my interatomic positions, the interaction between the subatomic particles, which are charged by nature, they also change. The intensity of the interaction between the subatomic particles, they also change. So essentially we have the like particles like nucleus and electron repelling each other, and we have unlike particles like electron and nucleus attracting each other. So when I change the distance between the atom, which is essentially only one thing I could change because I'm just considering two atoms, I see that the attractive, as I bring my atoms closer together, so R is the distance between my atom, and when I bring them closer together, my attractive force keeps on increasing. So of course, since it being attractive, we are using a negative energy by convention, and the repulsive is given a positive energy by convention. I don't know why, it doesn't make sense. Attraction should always be positive, but nonetheless. So attraction is treated as negative and the repulsion is treated as positive. So as I bring my atoms together, for most of the distance, the repulsive energy doesn't play any role. It was purely the attractive energy that keeps on increasing, that wants to get closer and closer and closer. But after a certain point, the repulsive energy shoots up, thereby preventing any further, let's say, proximus relation between my atoms. So I have two atoms. I wanted to consider their pairwise interaction, change the distance between them. I can see that they become increasingly attractive as I move closer and closer and closer because of the interaction between the subatomic particles. But beyond certain point, the repulsive force shoots up, or repulsive energy shoots up, thereby preventing me to get any closer. Now from the repulsive and the attractive energies, I am able to come up with something called as the net energy that has a typical trend like this. So two atoms bringing together, the net energy experienced by these two atoms can be expressed as the combination of attractive and repulsive energy, and we end up with a curve like this. Now, of course, there is this wonderful axiom as far as the systems go, material systems go. The material systems tend to move to a configuration of lowest energy. So we have our net energy plot here, and our net energy plot says this is the point where the two atoms are at their lowest energy. So it means these two atoms, when they are separated by this distance r0, they will be of the lowest energy configurations. So if I place my atoms, let's say at a distance r, and allow them to move forward and backward and monitor their energy changes, I will find that my atoms reach r0 and they stay because it is the lowest energy configurations of the atoms. So by this way, I'm able to, by just considering the interaction between my subatomic particles, I'm able to find out what is going to be my lattice parameter of the material. I'm not starting from anywhere else. All that I'm considering is my starting point is interaction between my subatomic particles, not the atoms themselves, but the subatomic particles, essentially the Coulombic interaction between the charges of the subatomic particles. Now, of course, R0 is not the only thing I could find out from these calculations. I can do something even bigger, meaning since what we have considered here is the energy that changes, this energy that changes with the position r, I can treat them as the potential energy. All that I'm doing is changing the position of one atom with respect to another atom, and the energy correspondingly changes, so I can refer to this as the potential energy. So that's the reason we refer to it as the interatomic potential, because we have pairwise interaction and the interaction changes with the position, we refer to it as interatomic potential. Now, since what we have is the potential energy or the interatomic potential, you can use this relation that stems from our Newtonian mechanics. We'll get to that. We have a wonderful way of deriving this. We will consider it if time permits in some other portion of this course. So if we know the interatomic potential and how it changes with time, interatomic potential energy and how it changes with the rather position. So that is exactly what this curve gives us, the dark black curve here. That is exactly what this curve gives us, change in potential energy with respect to position. Considering its gradient, now we are able to find out the force experienced by the atoms depending on their position. So what we essentially then have is, we started off with playing around with the distance between the two atoms. We were able to calculate or measure their energies, and from the different energies, attractive and the repulsive energy, we were able to come up with the net energy. And when we plotted the net energy, we were able to say there is a point wherein the energy is the lowest, so that is going to be the stable point, the interatomic distance. Now, using this trend here, that is how my potential energy, the interatomic potential changes, we are able to plot the interatomic force here. So the interatomic force is nothing but the first, or rather the derivative of my interatomic potential with respect to my position, and that gives me the interatomic force, and the trend of the interatomic force is shown here. And now at R0, my stable interatomic distance, my potential energy is the lowest. We have my minimum potential energy. So that means my force is going to be 0. So ultimately, the interatomic distance, the stable interatomic distance, is the one wherein the atoms experience no net force. The reason it is important for us to consider or move from potential energy, because both convey the same thing, but there is a reason why we can move from, or it is profitable for us to move from potential energy to interatomic force, is because if you consider this plot here, what we are essentially indicating is how the force is changing with respect to the distance between the atoms, how the force is changing with respect to the difference between the atoms. For instance, this is my stable position, and when I stretch my atoms, when I move my atoms away from this position, how the force is essentially changing is what is getting plotted here. So if you relate this to something that we consider macroscopically, meaning if you have a sample like this in a macroscopic scale, and if you are imposing a load P and there is an elongation dl, we will be able to rather relate P to that of dl. That is, my force is proportional to, or my load is proportional to that of my elongation, and my load by elongation is nothing but my stiffness. So what we essentially then have is, it is possible for me to relate my load and my elongation. These are proportional to each other during the elastic behavior when my load is sufficiently low and not so high. What I observe in the crystalline material is something called as an elastic behavior, and in this elastic behavior my load and the elongation are constant, and the constant of proportionality we can refer to it as stiffness S. Now this, what we see in the macroscopic scale, can be related to my force and intraatomic distance curve here, because my load in this case is nothing but the force, and in this plot here we are also considering force. And my dl, that is the elongation, is nothing but the change in length. In this case, the change in length is represented by r. R is the intraatomic length or intraatomic distance, and when I change my r, when I do something called as a dr, what I'm changing is rather the force experienced by the atoms. So ultimately, when I take the first derivative of my force, I'm able to calculate in a way the stiffness of my material. And on top of it, so this can exactly, or this can also be written as the second derivative of r square, so which will also be equal to my stiffness. So what it fundamentally means is, I'm able to calculate the macroscopic property of the material just from the calculation, just by understanding the interatomic behavior that stems from the interaction between the subatomic particles. So the subatomic particles, they interact, correspondingly my atoms begin to interact, and correspondingly the way my atoms going to arrange themselves is going to change, and this is ultimately affecting my macroscopic property that I see in my real life, that I am able to feel. So if my calculation of the interatomic or the interaction between the subatomic particles are accurate, then I will be able to accurately calculate my stiffness. I will be able to accurately calculate my intraatomic distance. This estimation of the interaction between the subatomic particles, they essentially stem from quantum mechanics calculations. So when we talk about the arrangement of the atoms in the atomistic scale, when we are considering how these arrangements influence the macroscopic properties, and when we consider how there is the characteristic configurations of the atoms and the characteristic distance between the atoms, all these are nothing but, or all these can be attributed to the quantum mechanics effect. So when my calculation about the intraatomic potential is accurate, again which stems from the quantum mechanics calculation, if they are accurate, then I'll be able to accurately calculate the intraatomic distance. Then also I'll be able to calculate the other parameters that are associated with the force separation curve or the force intraatomic distance curve. So therefore, while we are considering the crystal structures, while we are considering the lattice parameter, while we are considering the unit cells, while we are considering all these plots here, we are innately, or we are inherently rather, trusting the quantum mechanics calculation or the effect of quantum mechanics that are underneath it. So therefore, even though we have not so adequately considered it, our understanding of these interatomic of these arrangements of atoms and their interaction, they all stem from quantum mechanics. So with this, rather, the introduction to the quantum mechanics or the role of quantum mechanics in materials research and materials behavior, we will get into rather the foundations of DFT in the subsequent lectures. Bye guys.